Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of stellar evolution, and in particular, we're going to talk about why stars ultimately die. In a previous set of videos, we've talked about how stars form, we've talked about how stars produce their energy, and in this video, we're going to begin our discussion of describing why stars don't live forever. Now remember, stars are not actually living things, but they do have an evolutionary sequence that mimics that of life. They're born, they live, they die. And so in this video, what we're going to do is begin the discussion of why do they ultimately die. Remember here on the right, the sun formed. It is something that is in the process of going through the mainstream of its life. It's a main sequence star. And in the future, the sun is going to go through some dramatic changes and undergo a process that we call stellar death. And the reason why the sun will go through these changes, we'll talk about in this particular video. So let's go ahead and get started on that. In a previous video, we talked about what is called the proton-proton cycle. And remember that this is the thermonuclear fusion that the sun is experiencing every moment of every day to be able to produce the energy that we see. And if you recall, the important thing to understand is that the sun is turning its hydrogen nuclei into helium nuclei. And in the process of turning hydrogen into helium, something we call nucleosynthesis, the sun is able to produce the light that we see. Now, let's look at some numbers that go with this. They're truly staggering if you actually break down those numbers. Every single second, the sun is producing energy through the proton-proton cycle. And the amount of energy that comes from the surface of the sun will tell us how much energy the sun is producing at its core. Since the sun is not expanding or the sun is not contracting, the amount of energy that is leaking from its surface must be also equal to the amount that is being produced at the core. And so it turns out that the proton-proton cycle occurs 10 to the 38 times every single second. Now remember, that's a 1 with 38 zeros following it. So it's an enormously energetic as well as repetitive process happening over and over and over again every single second. But if you do the math, what that means is each and every second, 624 million tons of hydrogen is being converted by fusion into 620 million tons of helium. Hydrogen is becoming helium. Now, when you look at the difference between these two numbers, what that means is the difference between these two is 4 million tons. Now, if you recall from the last video, the sun produces its energy through the process of turning its hydrogen into helium, but some of the hydrogen that would normally become the helium is actually becoming the photons of light that comes out of the sun through the E equals mc squared equation. So 4 million tons of hydrogen is being converted to photons every single second. 4 million tons. So essentially, the sun is losing mass by turning it into energy, by turning it into photons. And so based on the quantity of hydrogen that the sun has at its disposal to be able to be used, we know that number as well. The mass of the sun is 1.99 times 10 to the 30th kilograms. Based on the total mass of the sun and based on the amount of energy that the sun is producing, the sun can actually sustain this energy production for about 10 billion years. So what that means is the sun will be on the main sequence, turning hydrogen into helium, and that energy that pours out that we see can be sustainable for a total of about 10 billion years. And it is often that you'll hear astronomers say how old the sun is. They might say something like the sun is a middle-aged star, or the sun is a star that's halfway through its lifespan. And the reason why we know that isn't just simply guessing, it's because we know how much energy the sun is producing. We know the process by which the sun is producing that energy, and so therefore we can predict how long it takes for the sun to go through all of its fuel. It's really no different than your car. If you have the type of an automobile that continually updates on your dashboard how many miles you have left until empty, it's doing the same thing. Your car understands, based on measurements, how much fuel your car is using as you drive down the road. It knows how much gas is left in the tank, and it just simply calculates how far can you drive before you're out of gas. So the sun is about 4.6 billion years old, with a total expected lifespan of 10 billion years. Therefore, the sun is about halfway through its entire evolutionary sequence, otherwise known as a middle-aged star. So the sun is halfway to the finish, and that's a good thing that we have some time left. Now, if you would come back to the idea of hydrostatic equilibrium, remember from a previous video, hydrostatic equilibrium is the balance between the radiation pressure caused by energy production coming from the core of the sun, balanced by gravity continually trying to squeeze the sun. And remember, the balance between these two is the fact that the sun is stable. As long as there's energy to be produced and radiation pressure coming from that energy production, the sun will stay very stable. The problem is that radiation pressure cannot last forever. There's not an endless amount of fuel for the sun to use. And so at some point, the sun will run out of its ability to produce energy. And in doing so, gravity will ultimately win this battle. It's important to remember, gravity always wins. It's just a matter of time before this happens. So speaking of that, let's put this into more concrete numbers. This is a slightly familiar looking slide. In a previous video, we had one that looked almost like this. But in this one, we're going to call it the main sequence timescales. And what that translates into, the main sequence timescale, is how long a star stays on the main sequence. If you remember from a previous video, we talked about pre-main sequence timescales, and that was how much time did it take for the star to arrive on the main sequence. What we're now going to talk about is how long will the star stay on the main sequence. If you read between the lines and connect some of these concepts together, the main sequence timescale means a couple of different things. The first thing that it means is how long will a star be able to turn hydrogen into helium and continue to produce energy. Another way to look at this is how long will the star be stable before it starts to die? How long will the star live? Now, if you remember, the HR diagram that I'm showing you here has been scaled down. This is the main sequence of the HR diagram, and we had superimposed the masses of the stars as you go down the main sequence. Remember, the mass-luminosity relationship allows us to do that. So the highest mass stars are up here, and the lowest mass stars are down here on this part of the main sequence. The numbers that I'm going to show you in red here are the main sequence timescales. Essentially, these numbers are how long the star will remain on the main sequence. So let's look at some examples here. These stars up here will be on the main sequence for about 10 million years. So their entire evolutionary sequence of formation, hydrogen becoming helium, and then of course having the problem of running out of energy production is over and done with in 10 million years. As we go down, notice the masses are decreasing, but the numbers of the years are increasing. So what I want you to notice is stars that are not very massive will be on the main sequence for an enormous period of time, maybe 100 billion years, 10 to the 11. So 100 billion years versus just 10 million years. So what this is actually telling us is that stars that are high in mass live very quickly, and stars that are low in mass live very slowly. And this seems to be a little bit of a contradiction. For instance, if I have a car and if I put a lot of gasoline in the tank of my car, I know that I'm going to drive a very big distance because I have a lot of fuel to use, and therefore I can use that fuel for a long period of time and I can go really far. But what this is suggesting is stars that have more fuel, remember the mass of the star is the quantity of its hydrogen, which is its fuel. This is suggesting that stars with more fuel live a shorter lifetime, whereas stars with less fuel live a longer lifetime. This seems contradictory, counterintuitive. It would be like putting less gasoline in your car makes you drive further than when you put more gasoline in your car. Well, this is ultimately resolved if you understand the entire idea. So let's put it all together. Stars that are very massive, remember, have a powerful force of gravity. And the powerful force of gravity is what makes the center of the star very hot. And so stars that are high mass have a very, very hot central core. And when the temperature is very high, the fusion process occurs very rapidly. And so it really just comes down to fuel consumption. Stars that are more massive have more gravity. More gravity makes the star at its core hotter. And when the core of the star is hotter, fusion happens at a more rapid pace. So stars that are more massive produce more energy because of gravity. Essentially, they produce more energy because they have to. More mass, more gravity, higher temperature, faster fusion, more energy comes out. So when you think about it, it is really gravity that is making the star make its energy. And remember that hydrostatic equilibrium says that if you want the star to be stable, the amount of energy that pours out has to create a pressure that's balanced by gravity squeezing in. And so stars that have more mass have more gravity. That's the squeezing force. The ability to fight off that squeezing force is the energy being produced at the core. So essentially it's kind of circular. A star that is more massive is going to be forced to produce more energy, and therefore to balance and have equilibrium, the more energy production is what fights off gravity. From a previous video, we saw the mass-luminosity relationship shown as this graph here. And if you recall, what it tells us is stars that are of a greater mass are also stars that are more luminous. And now we know why, because of gravity. So a star that is more massive is doomed to produce more energy to fight off that gravity, and as a result, will live a shorter lifespan. So the ultimate moral of the story is stars that are more massive live a shorter amount of time. The more massive the star is, the shorter its main sequence lifetime will be. Now what we're going to do is transition to the topic of how does the star deal with the problems that are faced when the amount of fuel that the star has runs out. Will the star die immediately? Is there a way to overcome this particular crisis? And in doing so, we're going to see how, once again, gravity plays a major role in understanding how the stars will deal with the end of their lives and what they can become if they can overcome these obstacles. But we're running a little short of time to squeeze it in this video. We'll begin it with the next one. I hope you'll join me.